Hello everyone. Let us discuss what are retaining structures, active earth pressure, and Rankine's active earth pressure theory. First, let us see why do we need a retaining structure. Providing flatter slopes is not feasible at all places due to space constraints, and the soil must need to be maintained at a slope steeper than that which is safe, and hence we go for retaining structures. A retaining wall maintains soils at different elevation on its either side, and soil is almost vertical behind a retaining wall. And without a retaining wall, the soil at higher elevation would have a tendency to slide, and that creates earth pressure. And let us have some examples for retaining structure. Here you can see a bridge abutment, and this is a retaining structure. 1 minute. This is a retaining structure. Here you can see some precast panels, and within that soil is being retained, and the ground is maintained at higher elevation with the help of this retaining structure at almost vertical condition. Here another example where along a hilly terrain you can see a retaining structure, and here the retaining structure is a gabion wall, and the ground is maintained at different elevations with the help of this retaining structure. And here is another retaining structure, and it retains the ground at different elevation on its either side. And you can see without maintaining a slope, you can maintain the ground or maintain the soil at almost vertical condition. Right? Now let us see what is earth pressure. The pressure exerted by this soil mass against the retaining structure is called earth pressure, and it acts in the horizontal or lateral direction, and its magnitude depends on few conditions such as wall movement, flexibility of the wall, soil property, and the drainage condition available. And what are the different types of lateral earth pressures? Based on the movement of your retaining structure with respect to soil, we have classified lateral earth pressure as active earth pressure, passive earth pressure, and earth pressure at rest condition. First, let us see what is active earth pressure condition in this video. Remaining things I will discuss in the further videos. Active earth pressure. So here you can see a retaining wall, and this is the backfill soil which is being retained, and the soil which is existing immediately behind the retaining wall will act as a solid wedge, and this solid wedge will in active earth pressure condition will tend to move in the downward and outward direction, and because of which this retaining wall will tend to move away from the soil, and we get the condition of active earth pressure, right? And here at this interface between the sliding mass of soil and the remaining ground, shearing action happens. And here you can see the shearing resistance has developed in the upward direction, and the sliding happens towards the downward direction. So by definition, as the retaining wall moves away from the backfill, the soil mass stretches horizontally and active earth pressure develops. And it is a state of plastic equilibrium condition, and soil mass will be on the verge of failure. Fine. In order to compute how much is the active earth pressure acting behind a retaining wall, Rankine has proposed his earth pressure theory. Let us see the assumption on which the Rankine's earth pressure theory is being constructed. The basic assumption are as follows. The soil mass is homogeneous and semi-infinite. And soil is in dry and cohesionless condition. And the ground surface is plane, which may be either inclined or mostly horizontal. And back of the retaining wall is considered as smooth, and the retaining wall must be in a vertical condition. See, the smooth retaining wall indicates that there is no friction between the retaining structure and the soil behind the retaining structure. And soil element is in the state of plastic equilibrium, which means it is at the verge of failure. Now let us derive how much is the active earth pressure based on Rankine's theory. First, let me draw. So let us consider, 1 minute. Let us consider a horizontal ground surface, and here is your retaining structure, which is almost vertical and smooth as per Rankine's theory. This is your retaining structure, and consider a soil element at a depth maybe h, and in the soil element vertically you will be having the vertical stress acting on the soil element in the vertical direction, and in the horizontal direction you can the soil mass is confined by the horizontal stress sigma h. So sigma is the v is the vertical stress and sigma h is the horizontal stress, right? And let us construct more circle for the soil element. So take sigma on along the x direction and tau along the y direction, and start constructing the Mohs circle. Since the soil is a cohesionless soil as per Rankine's assumption, the failure envelope passes through the origin, right? So here is your failure envelope, and this failure envelope is inclined at an angle phi, right? And initially your vertical stress will be in a higher condition, and your horizontal stress will be comparatively lesser than your vertical stress, because the wall tends to move away from the backfill and our active earth pressure condition means the horizontal pressure keeps on decreasing, right? Because the wall is moving away from the backfill, so the soil is being released, so horizontal pressure will keeps on decreasing and the vertical pressure remains constant, right? Hence this one will be taken as major principal stress and this one is the minor principal stress. So just translate them to our Mohs circle. So let us take sigma V, which is other way. You can take sigma 1 here, right? And this is your sigma H, or other way sigma 3 here, and draw your Mohs envelope. So this is your circle, Mohs circle. At this condition, failure will not happen. Now, what Rankine has suggested is just maintain the sigma V constant and just decrease the sigma H component, means decrease the horizontal pressure. How to decrease the horizontal pressure? Obviously, if the wall moves away from the backfill, the horizontal pressure decreases, right? because you are releasing the soil. So horizontal pressure decreases. So your sigma h will assume a lesser value, right? So now let us take this as your new horizontal pressure sigma h or horizontal stress sigma h. And to differentiate, let me take this point as A and this point as B. Now your new reduced horizontal stress will be in the point A dash, right? So, and your sigma B is constant in the second case also. So just construct the Mohr circle for the second case. Since I'm not using any geometric tool, my circle is not that perfect. Okay. So even now the failure did not happen. Now he is suggesting you to decrease the horizontal stress even further lesser. So if you decrease it further lesser, so it will go somewhere here. So let us take this new point as A double dash and draw your Mohr circle. So now you could see the Mohr circle just touches the failure envelope, right? So this is your failure envelope. And you can witness your Mohr circle has just touched the failure envelope, and at that juncture failure occurs. Hence the point PA is a significant point and we call it as active earth pressure, and the horizontal stress with respect to that failure condition is called active earth pressure. You can denote or you hence PA is the minimum earth pressure beyond which no further wall movement is being observed. Right? So now just translate your failure envelope and active earth pressure condition into a new graph just like this, and draw your failure envelope, and here you goes your horizontal axis as sigma and tau as your vertical axis, and this is your failure envelope that passes through the origin, and inclination of your failure envelope is phi, and O be the origin of your graph, and here is your Mohr circle at active earth pressure condition. So this is PA, and this is your sigma V point. So for easy consideration, let me retain this point as B, and let me take this point as just D. Okay, and let us take this point at which your Mohr circle touches the failure envelope as E, and C as the center of your Mohr circle at active earth pressure condition, and just draw a perpendicular that joins this point of contact and the center of your Mohr circle. Okay, and this forms a perpendicular, and if this angle is phi and if it is 90 degree over here, how much is this angle? Yes, it is 90 degree minus phi, and let me change the color of my pen. if this is phi and if this is 90 minus phi, and here goes a straight line, if this is 90 minus phi, obviously this is 90 plus phi. I mean to say 90 degree plus phi. Okay. And if you join, let me draw the circle perfectly. Yes. It's not that perfect. Let's see. And if I join DE, then this DE forms my failure envelope, and if this exterior angle is 90 degree plus phi, then this interior angle will be half of the exterior angle. I'll just draw this triangle separately. So this is D and here E, and if this is C, and here goes our 90 degree plus phi. So this is the exterior angle. Hence, the interior angle over here will be 45 degree plus 5 by 2. So half of the exterior angle. Hence, let me write with some other color. And hence, the interior angle will be 45 degree plus 5 by 2. Right? Now, our ultimate aim is to know how much is PA, right? Graphically, PA is equal to OD, right? So, PA equal to OD. In other way, I can write PA is equal to OC minus OC minus CD, right? And what is the speciality of CD? CD is nothing but radius of your Mohr circle at failure condition. Hence, I can write CD or DC whatever. CD is equal to CE, which is also a radius, is equal to BC, which is another radius, right? So, CD is equal to CE equal to BC. Fine. Now, consider a right triangle OCE here. So, in triangle O, I'll just make a partition here, OCE, how much is, our aim is to know how much is this radius, right? So, to get this radius, let me take sine phi dash or sine phi is equal to how much? Opposite by hypotenuse. So, CE by OC, right? And what is CE is equal to? CE equal to OC into sine phi. That's it. Now, coming back to our PA formula, PA is equal to OC minus CD. CD is again equal to CE, which is equal to OC minus sine phi. So, OC minus OC sine phi. Just take this OC outside. You will get 1 minus sine phi. Right? And now, what is your vertical stress is equal to? Vertical stress is nothing but sigma V equal to OB. I can write OB as OC plus BC. So OC just retain as such, And what is BC here? BC is the radius, and we have proved BC equal to CE. CE is nothing but OC sine phi. So OC sine phi. Just take OC outside, then you will get 1 plus sine phi, right? And we know that the ratio of horizontal and vertical stress is nothing but coefficient of active earth pressure. So Ka is equal to ratio of horizontal stress, which is Pa, by vertical stress, which is sigma V. Hence you will get OC into 1 minus sine phi by OC into 1 plus sine phi. So by simplification, you will get Ka as 1 minus sine phi by 1 plus sine phi. Right? You know what? Trigonometrically, if we simplify or if we convert this sign in terms of tan, you will get Ka is equal to tan square 45 degree plus 5 by 2. What is the speciality of this angle 45 degree plus 5 by 2? It is nothing but the inclination of your failure envelope with respect to the horizontal. Okay. And suppose for soil, generally in case of cohesionless soil, our phi value falls somewhere between 30 degrees. Then how much is your Ka? Ka is equal to 1 minus sine 30 degrees divided by 1 plus sine 30 degrees. We know that sine 30 is 1 by 2, right? So 1 minus 1 by 2 divided by 1 plus 1 by 2, which is 1 by 2 by 3 by 2, gives you Ka value as 1 by 3. This is quite commonly used. Just remember. That's it. Thank you.